Good afternoon. Welcome to episode number 10 of the ZoomTown experiment. This video started out very differently when I was planning it out. So I kind of need to back up to last week's episode number 9, where we covered a color sensor to detect colors. The purpose of that sensor was to read, so to speak, road signs from a robotic point of view, not from a human point of view. We see road signs as something like this in our real world, little stop sign here. But the robot doesn't necessarily have to read the word stop. It just has to have a marker somewhere to tell it to stop, or yield, or merge, or slow down, or go, something to that effect. Well, that sensor didn't work out very well. I found a number of problems with it. It was rather disappointing, but in retrospect, truly it was somewhat to be expected. Trying to detect colors in varying light conditions with a very simple sensor, I can see it being a very, very big challenge. There were a couple other issues with this sensor as well. Now, fast forward to today, or this afternoon I should say, and what I wanted to start out with, or the subject of this video, was to put, for lack of a better word or phrase, survey monuments on the layout. And how that would work, as you can imagine, a lot of what we're going to do for robot guidance is to use the marks here on the layout, line following. But that only kind of gives you guidance left and right how to steer, and especially on our layout, only for straight line moves. But it really doesn't give you any reference to some position on the table or the layout. So my mindset was such that we're going to be using a combination of line following, dead reckoning, encoder feedback, etc., for us to have a frame of reference for our localization so that the little zoomies know where they are in relationship to the whole area called ZoomTown. So my original plan for this video was to discuss how I was going to use a Hall effect sensor, and I'm currently using a little washer for this stand-in here, as a reference point by embedding magnets, where I'm putting this washer right now, to embed a magnet at the end of this line right here. That way, as the zoomie, say, backs out of its parking space and starts driving along this way, when it gets to that landmark, there will be a reference. Within the database, it'll know that this road will have a landmark here and here, depending on which way it's going. It could localize itself based on that landmark and where it started and get a very accurate position of where it is. That was the original concept. So I was going to go through, embed a magnet at the start and end of every one of these guidelines that we're using for line following. And that should have given us a great amount of information. Now, this isn't a new concept. If you go back and look into the historical records for robots that were in warehouses, AGVs, automatic guided vehicles, robotic guided vehicles, there's a number of different names they've had over the years. Well, the early robot guided or automatic guided vehicles in warehouses used magnets that were embedded in the concrete floors. And they were spaced very precisely apart and in a very specific path. That way, the robot, as it's going along, could see each magnet, knowing that each magnet was, say, 10 inches apart. It knew exactly where it was by counting those magnets, and of course, those magnets would be used for guidance. Now, in my situation here, we could have gone down that route, but it wouldn't have really solved a lot of other problems, and it would have made for a lot more work. But because of this problem this morning with last week's episode about that color sensor, that left me without a reliable way to detect or to get feedback from the environment as to what the Zoomie should do. Is this a stop intersection or just a flow through intersection? Do I have to go and stop and then go and be told to go? Those sort of things. So as I'm getting ready to film, I start thinking, Hall effect sensors are incredibly simple. It simply detects the presence or absence of a magnet, and its state is either on or off. There is no I2C interface. There is just simply on or off. And that gave me an idea. A very efficient way for me to add road signs, that sort of feedback or communication back to the Zoomie vehicle, I could embed additional magnets in the roadway so that the Zoomie would know, oh gee, I have to stop, or I need to go slow in this area, whatever it is I want to communicate. Now that's kind of hard with a single magnet with an on or an off. But I came up with a thought process, or an idea, if you will, how I can do this a little more effectively and get more bang for my buck out of these very inexpensive sensors. So I'll bring you in close on the layout here and I'll explain in detail what I mean. Okay, again, I'm using washers as my stand-in for magnets because I figured if I was playing with magnets, they'd all just jump together and join each other. But let's say my original idea was to put a magnet right there at the end of the line. And then, as mentioned, the car would back up, go across. When it sees that magnet, it knows that that's the end of the line, and from there it can figure out where it is in the whole layout because it knows its starting point. If it goes around a corner, it would know where the start of the line is and where the end of the line is. So that's a very simple feedback mechanism. But expanding that into road signs. What if I did this? Put a magnet there, and or a magnet there. With a magnet here, here, and here, all of a sudden I've got 3 pieces of information that can be fed back to the Zoomie. As it's coming up to this intersection, let's say it only sees this magnet or sees this magnet first. If it sees that magnet, that one's saying stop. Well, it may stop here, or probably has to be positioned a little further back so that it stops before the front of the vehicle is out into the cross traffic. So that could be a stop signal. We could have a magnet on this side and not this side. Well, that magnet being there says caution. Maybe that's a thing I would do to flag the Zoomie to slow down. I might have all 3 sensors in the same place. Well, if the Zoomie detects the presence of 3 of those sensors, that could communicate back yet another piece of information. All around, this gives me the 2 things that I really need, one from last week's episode and my current situation needing these monument surveys or milestones, mile markers, whatever you want to refer to them as. So I think we've got a cool workable solution here. It's very easy to drill into this plywood surface. I can embed the magnet in it. I can put a little colored sticker dot over it to indicate where the magnet is and what it's telling the Zoomie, just for human reference. And we would have a very robust system for helping with localization, with feedback from the environment to the Zoomie, and an easy method to construct all of that. So that's the concept. Let's go over to the bench and see if we can't put all of this into a little more practical test where we want to see if the magnets embedded in the surface can be detected by the Hall effect sensor and how easy it is to do that. Back here at the workbench, let's dive into our experiment for what we're doing with these magnets and the Hall effect sensor. The magnets themselves, these are I think it was 6 millimeters by 3 millimeters. I measured them up. They actually were a little thicker than that. They were almost 4 millimeters thick. For those of us here in the US, they're slightly smaller than a 1/4 inch diameter and about almost 3/16 of an inch thick. Now these are very inexpensive. Bought this whole box. They're 6 cents each. So spreading them out over the layout, very cost effective. Next up is the actual Hall effect sensor. That is this little thing at the end of these 3 leads. That's the actual sensor, and that's the component I'll be using on the Zoomy. I don't need the whole circuit board because the only thing the circuit board's doing is giving us a LED and a resistor to show us the state on or off. We don't need that. We're going to read that with the Pico W. But it did have a nice board and a header, so I could quickly throw this together to expand on my experiment a little more. For the Pico, I'm using a Pico W here. Just got it wired in with the 3 volts and ground, and then the feedback or the switch coming back is going into one of our GPIO pins. Now my thinking is such that we want to put the magnets embedded into the work surface, and that'll require me drilling a hole. I'm no stranger to that. That shouldn't be a problem. I got a little bit of woodworking experience to go along with this. So here I'm showing you how that bottom surface of the hole looks like. It's basically a flat bottom surface with a little dimple in the middle. And that type of drill bit's called a brad point drill bit. They're very common in woodworking, but it gives me a nice clean hole with a flat surface on the bottom for which to let the magnet rest in that hole. I suspect I'm going to use colored dots. All I have right now are little white round stickers for this little experiment, but eventually I suspect I'll have some green and yellow and blue or something like that so that we can identify the feedback coming from the road surface. In other words, we'll be able to, as a human, recognize what that sign is. For Hall effect sensors to work, we have to have the magnet oriented in the correct direction for the sensor. Now the sensor has a different shape to it other than just simply square. It's got 2 beveled edges here and here. And we've got a video showing how to work with Hall effect and all the details that go along with it. So if you need more information, I'll put a link down below for that. But what we do need to pay attention to, no matter what, is the orientation of the magnet. And we'll see it activate. And if I present the magnet the opposite way, it won't activate. I can go to the far side and eventually, no, she still won't get it. Now we'll get it. For as long as the poles are pointing in the right direction, we can get activate the sensor from either side. So what I want the sensing side to be pointed down on here, and that's for a good reason here. What I want to do is make sure that we can detect that sensor or that magnet all the way through this piece of wood. Now at this point I'm drilled about halfway through. This is close to 6 millimeters or close to a 1/4 inch, and I'm halfway through that. So let's see. Okay, at this point we're not seeing it. Oh, there it goes. We can see it from here, kind of. Let's flip it over and let's do a little metal detecting or magnet detecting. Okay, our magnet is right in that area. And it can detect it quite nicely. Oh, there he is again. All right. And I'm coming up off the surface about 4 or 5 millimeters as I'm looking at it. It's kind of hard to see in the video. You're looking at it from above. And we're not getting anything that way, but if I turn it that way, we can detect it from here as well through that little paper sticker. But my real concern, I wanted to make sure that we could get through enough of the wood to still catch that magnet. Now what I'm going to do is I'm going to put some more magnets in here and then make sure we can differentiate each magnet from the others. I don't want to bring this sensor up here and it's detecting that magnet and so forth. So give me a minute. I'll fast forward through this and we'll get the rest of these set correctly. All right, now let's see if we can go about finding them. There's one. I think, yes, you can see that on camera there. We got one, goes off, we hit the next one. We're right in between them, hits the third one, right in between it, fourth one, fifth one, and sixth one. So that tells me a lot right there. It tells me I can have these magnets spaced as close as a 1/2 inch or 13 millimeters to each other and still differentiate from one to the other. It also tells me I can sense through about 3 millimeters or 1/8 inch of hardboard. This is a little more dense material than the plywood that the layout is made out of. So the sensor can do exactly what I want it to do. And there's one more thing I need to figure out. I want to make sure I can read this sensor fast. One of the problems with that color sensor that I didn't like, it took about 10 milliseconds to get a reliable reading out of it. And in truth, that was kind of questionable to call it reliable, but it was fairly consistent. So let's dive into some of the code for this. Let's write our little routine to measure how long it takes to take a measurement, and we can go on from there. As I have been doing with the code, I want to measure the time it takes to read a sensor or perform some action. That's going to be very critical as this whole project comes together. Now in here, I've added the code, but I'm going to take away some of the original code. The real issue here, or the trick for checking this time, at the beginning of my read, before I read the sensor, I'm going to say ST, start time, equals time ticks underscore microseconds. That'll record the current microseconds reading. I don't want all of this. That's not really what I need in the form of a measurement. All I really want to do is know what that value is, because I will perform an action based on state. In this case, I'm using the variable state to hold whatever this input sensor is giving us. So literally start time is here. We're going to skip all that. We'll execute the state. We'll record the end time in ticks microseconds. And then RT is the calculated difference between start and end. And here we'll print out the state and the read time in microseconds. We'll sleep for a little bit and repeat the loop as we're doing this. So let's see what we get. I suspect it's going to be very fast. You'll notice the first one was 100 and some microseconds. That's very typical, just like analog readings too. The first one's almost always kind of rubbish. And here we go. We're averaging about 24 microseconds. That's incredibly fast. I'm really liking that. Now keep in mind, we've got to multiply that times 3 because we'll probably have 3 Hall effect sensors to read 3 magnets. So that'll give us 75 microseconds, well under a millisecond. So I'm really, really happy with that result. It seems to be incredibly reliable. I mean, it's on, off, very easy, very simple. I don't think it gets much better than that. And it's solving two problems. This is one of those make lemonade out of lemons situations. I started out this morning planning this video to just simply be how to set up a survey marker or a milestone on different locations on the layout. And we ended up expanding this simple sensor into solving another problem, and that is to provide feedback from the layout, the road surface, telling the Zoomy what it may need to do. Very cool. I'm really, really happy it all turned out this way. Of course, I'll continue to explore in the background on that color sensor from last week's episode. If that evolves somewhere, we'll reincorporate it. None of this stuff is cut in stone. Once I make a decision, it's good forever. No, this is an experiment. We can keep playing. Now next week, I've got another really cool sensor. It's called a time of flight sensor, so we're going to dive into that. That'll be used for a collision avoidance system, so that the Zoomy, as it's moving along, if something pulls in front of it, the sensor can say you're X number of millimeters or inches away from it, deal with it. So hopefully that one will work out better than my color sensor. That'll wrap it up for this week. I look forward to seeing you in the next episode.